Okay. We continue our lectures on stochastic analysis, and now we are considering the following situation. We have the space RD, and Gaussian standard vector here. So that psi has maybe it's better to say that psi1, psi are standard Gaussian vectors. And we are discussing equilinear expansion, chaotic expansion for this case. So if we have random variable alpha, which belongs to L2 sigma psi, then we are asking about its expansion with respect to orthogonal polynomials with respect to this random vector xi. And last time we wrote some form of these polynomials, and maybe some of you face that okay, it is very similar to the one-dimensional case. There are nothing new, and you know, such a person will be right at 50%. Why? Of course, we will use, and we use already, one-dimensional results. From these results, it follows that polynomial are dense with respect to this measure in RD, because it's a product measure, and polynomial are dense with respect to one coordinate measure. Secondly, we know that they are Hermite polynomials, so then we know that we can organize orthogonal basis in this space. Just multiply the polynomial Hermite polynomials from different coordinates. So the answer is the following: we have alpha, which is equal the sum from n equals 0 to infinity, and here is the sum in plus id equal to n, and here is h d, and here is h e1 from psi1, and so on, h e d from psi. We easily get this representation, and yes, there are nothing new. Moreover, one can say, okay, I can introduce a differential operator. Why? Because one can differentiate with respect to the different coordinates, and we know the result. So one can introduce the stochastic derivative of the variable alpha, and it will look exactly like a one-dimensional case. But now we face multi-dimensional graphs. First one, if in one-dimensional case, one can say, if alpha has stochastic derivative, then alpha can be represented by the function from xi, which is at least continuous. This is because the Sobolev embedding theorem, which says us that in one-dimensional case, Sobolev functions are continuous. But in multi-dimensional case, it is not true. So, first of all, we will introduce stochastic derivative, but introduce the stochastically differentiable random variables can be represented by the non-continuous function of vector psi. This is one. Second is much more sufficient. Why? Because maybe you remember from the course of probability that if I use a rotation, so if I apply such matrix which has the following property, u equal u minus 1, then u psi, this new vector, is also standard Gaussian vector. And it is evident that if alpha is measured with respect to psi, it will be measured with respect to eta. And one can ask, what will be the expansion of alpha with respect to eta? Maybe some other coefficients, of course, but why? What coefficients will be written here? So we have to find some way to write eta-Wiener expansion, to write stochastic derivative, to discuss weak product in a not coordinate way of thinking. Maybe this is common, by the way, for step from algebra to functional analysis. We always want to have non-coordinate way of thinking, way of writing things. So let's do it in this case, because it will be much more easy to go to the infinite dimensional case from this one. So I will introduce the tools which allow us to understand what happened in this multi-dimensional case. And maybe you will recognize it because it's again is stochastic exponent. So now let us introduce stochastic exponent. It depends on the vector lambda, and it is the exponent of lambda psi minus 1/2 of norm of lambda square. And as you can see, this is a non-coordinate way of writing. Yeah, of course I can expand it using coordinates, but I will not do this. And in this case, you see just the function, which is which is like stochastic exponent in one-dimensional case, and we will use it. Why? Let's see. First of all, let us find expansion of stochastic derivative in multi-dimensional case. Is equal to the sum. Here we have n equal 0 to infinity. Here we have sum E1 plus ED equal to n. Lambda E1 excuse me, lambda 1 in E1 power divided by E1 factorial lambda d ED power divided by ED factorial. And then H E1 from psi1, H ED from psi d. And from this formula, we can see that we can easily find the expression of this expansion just taking derivatives of stochastic exponent with respect to lambda. Moreover, this is exactly the stochastic derivative of order n of stochastic exponent with respect to lambda. So now one can imagine that I can introduce stochastic just derivatives of stochastic exponent like n derivative and then I know what is it. Yes, we just write the sum 1 plus d equal n. There is now let us consider the expansion for random variable alpha. As we have seen, it must have expansion of this kind. H d psi d, and now we can introduce Fourier linear transform exactly as we did it in one-dimensional case. So let us consider tau alpha from lambda. It will be equal to expectation of alpha multiplied our lambda, and one can see that it will be equal to the following equal to sum of n equals 0 infinity. Here is the sum from E1 plus ED equal to n, and here is AE1 ED, and here is lambda 1 E1 power lambda d AD power. This is due to the property of Hermite polynomials that we remember that norm of Hermite polynomial, for example, HE1 is equal to E1 factorial. So it will be constant. And now we see that here we have a very interesting summand related to variable alpha and to our stochastic exponent. And the form of this summand gives us the idea how to write in a non-coordinate way the expansion for random variable alpha. Namely, let us introduce multi-dimensional operators, say A n, which act on Rd multiply on Rd and times to R, and is linear with respect to every coordinated continuous. Then I can write this AN using coordinate form exactly as using such coefficient A, E1, ED. Because AN, if we use coordinate form, must be written as follows. We take E1 times the first coordinate, 2 times the second coordinate, and so on. And if we suppose that AN is symmetric, then we have one-to-one correspondence between AN and such set of coefficients. Moreover, I can say that AN from lambda lambda will be exactly this. From this point of view, one can say that when we consider random variable alpha, which is square integrated measure with respect to our initial standard Gaussian vector, then it occurs that alpha is equal to the sum from n equals 0 to infinity. And this sum I will denote by the form an from psi, psi, psi. And how it must be understood? We just have in any basis coefficients for an, like this one, and then substitute with these coefficients, substitute powers of psi by the exponents. From this point of view, it is useful to recall that we introduced in one-dimensional case the weak product. And now it's time to introduce it there. So when we have such expansion, I will say that alpha, and here weak product beta, where beta have the same representation, sum of n equals 0 to infinity bn psi, psi, psi. That weak product alpha beta is equal to sum from n equals 0 to infinity, sum from k equals 0 to n. Here is symmetrization of the tensor product of A, K, B, N minus K, psi, psi, psi. Why I need here symmetrization follows exactly from the definition of our expansion. You remember that we say that let AN be symmetric, let BN be symmetric, because in this case, we have one-to-one correspondence with the coefficients if we write it in coordinate way. So I suppose that AN and BN are symmetric. But the tensor product is not symmetric, of course, because AN and BN are arbitrary. So we have to make symmetrization. Let me emphasize this. We have symmetrization, and after this, we can apply vector psi, and then have a such sum. Of course, this sum not always is convergent, but we define the product to be equal to the sum if this sum is convergent in two sets. Moreover, one can check that now we can easily calculate the expectation of random variable alpha, of course, is equal to alpha zero, a0, and expectation of alpha square is equal to the sum from n equal 0 to 50. Here is norm an square, but special norm. I will say here n, and let me write this norm more precisely because it is important for future consideration. This is a Hilbert-Schmidt norm of this form. Norm an square is defined as follows. Now let us take arbitrary orthonormal basis and then take the sums equal 1 to excuse me, we have here n to d, and here is a n e1 e1 e n square, where this is orthonormal basis. It can be checked, and by the way, it is a very good exercise, that the definition of this norm does not depend, that the value of this sum does not depend on the choice of the orthonormal basis. And this value is called Hilbert-Schmidt form of the multilinear for an. So we have such relationship exactly as in one-dimensional case. And now we can go to the stochastic derivatives. Namely, we will define stochastic derivative for the random variables. You remember that here we use the property of Hermite polynomials that with respect to the differentiation, they behave exactly like powers. So now let us have a random variable alpha, which has the following expansion: an psi, and define its stochastic derivative. Because we have some analogy with the usual derivative, we expect that now, like gradient, it must be not random variable but random vector, and it is true. Let me write the formal notation, and then we will discuss. So I will define d alpha as a random vector such that if I multiply on some vector from our space Rb, then I must get the following sum n equals 0 to 50, and here is an h, and then psi. So we have here n minus 1 psi. So in this case, we will get Hermite polynomials here with degree which is less on the 1 from the initial Hermite polynomials. Yeah? So we have such an expression. Of course, it's valid when the series converge, and it is linear with respect to h. So one can define d alpha as a random vector such that formally one can say that d alpha is the following sum from n equals 0 to 50, and here is n, an, point psi, 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 psi. But this formula is not clearly understandable because we have to remember that substituting for xi, we must substitute powers of coordinates by Hermite polynomials and so on. But for writing, sometimes it is useful. So we define stochastic derivative for random variable alpha, and now it's time to say that most important properties of stochastic derivative are exactly the same as in one-dimensional case. So we have the statement that D is closed linear operator. We have the statement that D is densely defined, of course, because we can substitute here not infinity, but some final values. And we have chain rule. So we have all good properties for this stochastic derivative. So in this way it is produced. Only as we have said already, we have to know that the function which have stochastic, the random variable which have stochastic derivative is not now represented by the continuous function. It is not true because we have not such embedded theorem. In order to have continuous representation of alpha as a function from initial vector psi, maybe it is understandable, we have to require several stochastic derivatives from alpha. Now let's go further and introduce the adjoint operator, which we call product with psi. Now it has the same form, so we introduce adjoint operator to D. It works like this. We just have expectation of d alpha multiply on some random vector beta. It must be noted that now this adjoint operator is acting from the space of square integrable random vectors to the space of square integrable random variables because of d is a random vector. So we have such a relationship alpha multiplied by e beta, which can be understood as integration by part formula for Gaussian measure or standard Gaussian measure. So one can get the expression of beta in the coordinate form. If we suppose that beta is represented like f from psi, where f is C1b, we remember we denote in such a way functions which are one type, continuously differentiable, and are bounded together with the derivative. So we have such a function f, and in this case, it will be a good exercise to check that E from beta is equal to sum from k equal 1 to d, fk multiplied by psi k minus d fk d psi k. So here, because of we have sum, one can recognize the divergence operator, and this new term arises due to the fact that we have not Lebesgue measure but Gaussian measure. In case we discuss integrating by parts formula for the break measure, we have exactly the following answer. Yeah? So this is the answer in Hauschen case. And you can see here that again, this divergent, this joint operator is a differential from one point of view. But because of fk are functions, we have here possibilities to avoid these terms. And let me just give you an example, and in the future we will see that it will be useful. So let us suppose that our variable beta is organized in the following way. That beta is equal, to here F0, which is just number, then F1, excuse me, maybe this is not a good notation, F1 here, which is just number, F2, which depends on Xi1, F3, which depends on Xi1, Xi2, and so on. FD, which depends on Xi1, Xi d minus 1. Then, if we apply this procedure to our special random vector beta, what we will get? We'll get the following. We'll get the following. We'll get that I of beta is equal to the sum from k equal 1 to d fk psi k. That's all, because this derivative is equal to 0. And maybe now you understand that in the future we will consider such functions where instead of psi we'll have increments of Brownian motion, and instead of this sum we will have approximation to the Ito stochastic integral. And this is a very nice thing that we will see in infinitely dimensional case. This joint operator to stochastic derivative, which is actually generalization of this differential operator, can give us the answer like Ito stochastic integral. So now we are working with a finite dimensional case, but it is time to go further and let us consider infinite dimensional case. Okay, so from now I will consider Hilbert space H is set up Hilbert space and I will suppose that the dimension of H is infinity. The classical examples for us are L2 small or L2 capital, 0, 1. So we know a lot of examples of such space. I want to have the same construction as before in this case. So let me recall you what elements of the construction we have. We discussed random vector psi, which is standard half. We discussed L2 from this vector. We discussed expansion. Alpha is equal to sum from 0 to infinity an from x I. We discussed stochastic exponent. E lambda is equal to E lambda xi minus 1/2 of excuse me, 1/2 of the norm of lambda. Okay. We discussed stochastic derivative. The alpha equals something n equals 0 to infinity an sin xi. And we discussed the operator, which is a joint of the stochastic. When we start to consider infinite-dimensional case, we have a problem from the very beginning, because we must have the Gaussian random vector, or it's better to say Gaussian random element H, with norm excuse me, with the covariance operator equal to identity operator, because here it was identity matrix. So let's try to consider such kind of random element. What will I'm trying to write this element in coordinate form. So let's fix some orthonormal basis in this space H. Say En is orthonormal basis in H. Then one can look for a random for standard random element as follows. We just have this infinite sum from n equal 1 to infinity psi n e n, where psi n is what? Is IID sequence of standard normal values. And then the first question which we have to answer is following. Do we have a really convergent series? Let us try to understand this. So we understand that this series converge if and only the sum n equal 1 to 50 of psi n square is less than 50. But you see, they are independent and IID having non-trivial distribution. So why we have to expect that they are at least converging to 0? It is not understandable. And you easily get the following result using Borel-Cantelli lemma that the following holds, that with probability 1, the upper limit when n tends to infinity of n is equal to plus infinity. For example, please check this. Well, we have a lot of differences. One can justify the limit like in the both part of Borel-Cantelli. So we can say that moreover probabilities that upper limit when n tends to infinity psi n divided by a square root of logarithm of n is equal to I think 1/2 is equal to 1. Just check this, but it is a constant which is separated from 0. So due to this, one can say that there are no such signs as we considered. So what is the right way of thinking? Maybe we have to stop and forgot about such nice construction as we did in a finite dimensional case. It is not true, because as we recall the formulas, we don't need psi itself. We only need its coordinates or its products with the vectors from our space. Just recall the stochastic exponent. So let us try to imagine that we have those formals and try to consider this inner product H psi, where H is a now deterministic element from our hyperspace. So what we will have? In coordinate form, it is equal to the sum from 1 to infinity, Hn psi n. And now is a crucial moment. Let's see on this infinite series. Hn are coordinates of our elements of hyperspace. So due to Parseval's identity, we know that sum from n equal 1 to infinity Hn squared is less than infinity. Then, using Kolmogorov theorem about the series, one can say that this series converge with probability 1, converge in L2 sense. So this sum is well defined. The sum is well defined. Due to this, we can go further. We can consider that inner product with inner products with these random elements, even when we know that this random element does not exist. We will say that it is a generalized random element. It comes from the generalized functions and looks like the same situation, because when we have a generalized function, we have only its action on the test function, and it is not really a function. Now we have the same situation. We have its action on the fixed deterministic elements from H, but there are no such random element in H. So let's go further, and now one can imagine that maybe we will have the expansion for random variables which are measured with respect to psi. It is true, and in order to do this, let me recall you the simple statement from the probability codes. Now let me introduce this sigma psi, which is of course a sigma field, smallest sigma field generated by psi1, psi n, and so on. And let me introduce Fn, which will be the smallest sigma field generated by psi1, psi n. Then, of course, I know that sigma psi is the smallest sigma field generated by the union from n with infinity Fn. I know that Fn is included in Fn plus 1. And due to this, I have a following property. If I consider alpha, which belongs to A2 sigma psi, then I can check the following. This is a Levy theorem. I can check the following. That the conditional expectations with respect to Fn converge in L2 sense for alpha when n tends to. So we have this statement, And maybe you understand that using this statement, we can proceed as follows. Let us consider this random variable. It is measured with respect to finite number of coordinates of our generalized random element. Then we will get expansion. Then we will discuss the properties of this expansion and prove that when n tends to infinity, this expansion tends to some good formula. So in this way, we will get logic expansion for random variable, which is measured with respect to our generalized random variable. And by the way, this is a way how we can expand all our results, all our definitions, which we have from finite dimensional case to infinite dimensional case. And we will do this next time because it is from the logical point of view, good time to stop here and do everything next time. So for today, this is all. Thank you for attention. And maybe somebody have questions or comments, please.
Yes, I have a question. Could you define what symmetrization of a tensor product means?
Oh, yes, it's a good question. So suppose that we have just multilinear form. Yeah. So we have, for example, an which acts from R D multiply on D and times to R. So what will be its symmetrization? Lambda A n it's acting on for example vectors P1, P n is defined as follows. This is one of them. The sum of all permutations sigma from the group of permutations, and here is an. Here is phi sigma 1, phi sigma of n. This is a definition.
Okay, thank you.
You're welcome. And it leads to very interesting formula related to the norm of this adjoint operator. We will see what will be the answer here. What is this? What is this in general case? And we will see how this procedure reflects in the answer. But as I think it is good time to stop because we will go to especially infinite dimensional case. So we will see it next lecture. Okay. So if there are no any other questions, thank you and see you next week. Bye.